All right, welcome back. Hopefully this is welcome back. This is truthfully 11.1 part 2, and I got to get a little focus job done here. I think we're good now. A little bit of a lag, but I think everything's going to work out for us. So we were talking about using normal distributions. We were talking about means and standard deviations, and we went through a number of example problems from your note packet. And everything so far was just really clean. In other words, we were just, when we set up this problem and we had a mean of 33 and we had a standard deviation of 4, got us to 37, 41, 45, back to 29, 25, 21, and then all of those values were exactly located at standard deviations. And then we did a firehouse problem. And once again, all of our standard deviations, standard deviation of 1, we never talked about what would happen if the goal of the fire department is to reach the scene of an emergency in 5.7 minutes or less. Now, 5.7 minutes wouldn't put us right on one of our standard deviations, so everything we learned about this wasn't really of much value to us. We could only do like really crude approximations. Now the best news for this is when you're given a set of data, like in this firehouse problem, you would probably be entering those in calculators typically. They wouldn't normally tell you. I mean, that's the bad news. You're going to have to do some of this. They're not just automatically going to, in a real world problem, give you the mean and give you the standard deviation. You would find those in your calculator. But the good news is you just use a list to find that, and as soon as you found it, you could find probabilities if we're just fractional deviations away, not a full standard deviation and another one and another one. But just any amount of deviation, your calculator will do that. However, for our purposes right now, we're going to go through what's called a z-score, and you'd do that anyway if you weren't doing it by hand. But let's talk about this. The standard normal distribution. The standard normal distribution is the normal distribution with the mean of 0 and a standard deviation of 1. That's for convenience. The formula below can be used to transform x values from a normal distribution with mean mu and standard deviation sigma into z values, where now z is our standard deviation. Okay, why does this work? Let's consider for a second that we have a mean score of 70, for instance. And let's say our standard deviation is 6. So if we're 6 units out, we're 1 standard deviation. 12 units away from 70, 12 steps away, we're 2 standard deviations. But what if we were 7? What if we had 77? How many standard deviations is that away? Well, it's more than 1. It's 7 units away, and 6 units is a standard deviation, so it stands to reason that 7/6 we're 7/6 standard deviations away. Well, what did I do? I took 77, subtracted 70, and got 6. So in the problem we talked about yesterday, as far as, or on the previous video, part 1, excuse me, the population, let's say the mu value population for Hananiga girls is 5 feet 5 inches, and the standard deviation is 2 inches. Let's say we spoke about that, then what we would do here, let's say we had a 5 foot 8 inch girl, and we're adding her to our data. We'd take 5 foot 8 inch minus 5 foot 5 inch, we get 3 inches, and we divide that by 2, we get 3. Oh, we're 3/2 or 1.5 standard deviations away. So that is where the z-score comes in. So our z-score is useful because let's say we have a z-score of 1.3. If our z-score is 1.3, here's what it means. Put it on the graph. Here's 1 standard deviation, here's 2 standard deviations. We're like right in here. This table, here's 1.3 standard deviations. This table will find the probability that z is less than, it will find this area. under the curve if the curve has a total area of 1. So we just look up 1.3. Here's 1.3. That would be 1.3. That's 0.9032. So the probability equals 0.9032. Well, I'm certain you can figure out, what if we wanted the population to the right of a z-score of 1.3? That would just be probability equals 1 minus 0.9032. Okay? So this would be a really good time, as I say often, to pause the video and try problem 24. Welcome back. So since you've restarted your video, scientists conducted aerial surveys of seal sanctuary and recorded the number of seals they observed during each survey. This has actually kind of been in the news, sort of, lately. At Cape Cod, I just read this today. They do aerial views, helicopters, and they just count great white sharks, and that number has been increasing quite a bit. I suspect if the number of seals increases, shortly after that, the number of great white sharks is going to increase, and that's part of what they discussed in that. It was kind of interesting that that just popped up in this problem today. So here we go. The number of seals observed were normally distributed with a mean of 73. So normally distributed with a mean of 73 and a standard deviation of 14.1. So I'd go over 14.1, over 14.1, over 14.1, left 14.1. Let's go 3 standard deviations, as we've been apt to do. Now let's think about this for a second. Find the probability that at most 50 seals. Well, if I go down by just 14 and not even 14.1, this is going to get me to what? Well, I guess I'll just do it 58.9. 58.9. And this is going to get me down 14.1. That would be 44.8. And we want to find the probability that at most 50 seals were observed. Well, 50 is going to be somewhere in here. Somewhere between 44 and 58. And at most would mean we want this probability, or we want this area under the curve over there. So it doesn't hit. It's not canned like these previous problems that we had, that everything lined up on a standard deviation. So how far are we away from 73? Well, we go 50 minus 73, here's our z-score, divided by 14.1. That's how many standard deviations we would be away if we converted this to our standard deviation is steps of 1. So a real quick check on the calculator on that, and we get z is approximately negative 1.63. So we go to our z-score, and first off, it's kind of nice to understand it's not a very big probability. Much more of the graph is over here. In fact, if I drew this to scale, it would even look more severe than that. Negative 1.63. So I look up negative 1, follow it across to 0.6, and I'm between these two. Closest to this. So it would not really be technically wrong here to say that we end up the probability equals 0.0548, but it probably wouldn't be wrong to say the probability, should say approximately, is approximately, well, I guess it could be a little bit less than that, maybe 0.05 or 0.051. For our purposes right now, we'll just use whatever it rounds to, and eventually we'll be having our calculator do this for us. Back in the old days, we'd have to take these values and extrapolate, and which was quite a long process. Could be quite a long and drawn out process to get accuracies there based on slopes and things. But our calculator is going to do a lot of that heavy lifting for us. So for right now, I would be okay with you saying P is approximately 0.0548. Now, what if it said at most? Well, it does say at most. Find the probability at most 50 seals. What if it said at least 50 seals? Well, now they're talking about that data, that would be 1 minus 0.0548. Okay, and hopefully that does it for you. Homework assignment is attached to this handout if you got it, but that's our homework assignment. And real quickly, you are welcome to, if you would like, for this, use this assignment for some of the answers on here, but anything else that they give you where they don't have the normal curve drawn, I'm going to require that you have the normal curve drawn for the rest of that assignment. And one more note, it looks like we got through 23, and if we just scan 20, 21, 22, 23, where here's 24, 25, 26, 27, here's 29, I just cut and pasted it on here. So hope that helps, and we'll be talking with you soon.